All right, folks, this is our angled forces and equilibrium lecture. So if you recognize this picture and you're like, I already listened to this, psych, it's the rest of the slides that you didn't see the first time. All right, so quick review. When a vector is crooked, it means it's got to pull, we're talking about forces here, so it's got to pull horizontally and a pull vertically. So if the total force is the hypotenuse, then the vertical part is stop signs are vertical, so it's going to be the force times the sine of the angle. And since coastlines are horizontal, the blue part of the force, the right pulling part of the force, is the force times the cosine of theta. Okay, so that was the old stuff. Now, if you study mechanical engineering, you can take an entire semester's course looking at like suspension bridges or this pulley system, or even like if you're designing a chair, your chair has 4 normal forces, you know, for the 4 legs, and because your weight isn't distributed evenly, you might want to calculate, you know, what the pressure is at each leg. All right, so this is how you would do that. So the first thing I want to make sure you have in your notes is definition of equilibrium. Okay, and equilibrium means when you add up all the forces, you get a big fat 0. Okay, so if you like the phrasing better, that it means the forces are balanced. How do you know if something's in equilibrium? The easy answer is if it's at rest, the forces are balanced. That's pretty straightforward. People get that. The second case, though, is tricky. It could also be traveling at constant velocity. So if you remember on that pretest that you all took, there's a question about an elevator, and it asked you when it was going upward at a constant speed, however much the speed is, doesn't matter, as long as it's constant. And the question asks which is bigger, the tension in the cable or the weight. And because it's going up, people think, oh, the tension must be winning, but if the tension were bigger than the weight, what would this object be doing? It would be gaining speed faster and faster and faster, and it would be accelerating, not going at a constant speed. All right, I know people still get this question wrong, even though I address it every year on the post-test. So just think about as this like a restart the clock problem. In period 1, the tension 1, boom, got up to whatever speed you want to get to in the elevator. Then it kind of reduced the stress, and now these 2 forces are balanced. So do not fall into that trap. Constant velocity also means the forces are balanced. Okay, this is an equilibrium if it's not gaining speed, if it's not accelerating. All right, and I forgot the subscripts on these formulas. Definition of equilibrium implies if it's constant speed or at rest horizontally, we're going to say the sum of the forces are 0. If it's also forces are balanced vertically, we're going to say the sum of the up and down forces add to 0. Okay, and this is going to give us a system of equations that we're going to use to solve for what we don't know. All right, it is entirely likely that a problem might be accelerating horizontally and not vertically, or vice versa. Again, that's, yeah, you can use the clues in what's happening to understand whether that's true or not. But the first, what we're going to practice now is both balanced. Okay, yep, I already said that. If you want to pause the video and write any of this down, go ahead. All right, so this is a classic problem. Please copy this to your notes. And I think I scanned this in from your textbook. They give you the mass of the picture, and we need to find this tension and that tension. Okay, since we're going to have two equations, horizontal and vertical, we're going to have two unknowns. Okay, so the first thing you want to do is draw all the forces. This problem already has that. The next thing you want to do, not mandatory, but super helpful, is label plus, minus, plus, minus. And then we're going to break this T1 down into how much is over and how much is up. And by alternate interior angles, that is also 30. So, hang on, sorry, I'm changing the color. So this leg right here is T cos 30 because coastlines are horizontal, and this little pink up is T1 sine of 30. And then T2 has a little bit left and a little bit up. And those are going to be T2 cos 60 and T2 sine 60. All right, and then this picture is not moving, so I think it's helpful. We know that it's in equilibrium. So these two are equal to each other, so you can make tick marks to remind yourself of that. You can't do the same thing vertically because the green plus the pink up equals the red, magenta, pink down. Okay, so it's this green vector plus the pink vector. Maybe you can imagine adding the green to the pink and you get something the length of W. Okay, that's what the balanced means. Oh, I know what I want to say. So the last thing in terms of the diagram is, first of all, these tensions don't have minus signs because, well, so the pink vectors are both positive, but look at this green vector. T2 cos 60 is actually negative because it's pointing left. I love the system. This green vector is pointing to the minus sign. It's telling you it's negative. This pink vector is pointing to the positive sign. It's telling you it's positive. But the T2 cos 60 is negative, but the T1 sine 60 is positive. All right, so the actual tension doesn't have a minus sign because part of it's negative and part of it's positive. All right, so when they say find the tension, they're just asking you to find the magnitude of tension and not the direction. Okay, because the only thing the minus sign means is direction. All right, so we have our mise en place. We have the picture all set up. Now we're ready to actually start cranking out some numbers. So what you're going to do, this is not optional. Not optional at all. You've got to make two columns, horizontal and vertical. I don't have enough space on this sheet to do both, so we're going to just do the horizontal first and then carry that over to the vertical. All right, so you've got to label your columns, and you have got to start with a statement that, sum of the forces either equals MA or, in this case, 0. You cannot just say this equals that. This is a free point on the AP for saying I understand that the Newton's second law is true. It's a special case. It adds to 0. You've got to do that. You've got to say what the direction is, and you've got to say that the sum of the forces equals 0. Okay, and then you might want to bring a highlighter in to the test or on your homework and highlight every force after you've addressed it so you don't forget them. So the rightward force minus the leftward force, nobody's winning, they add to 0. Okay, doesn't seem very satisfying yet. We need to solve this for T1 or T2. It doesn't matter. Each one is equally nothing squared, so it really doesn't matter. I just happen to solve it for T1. I reckon you can leave this as cos 60 and cos 30, but sometimes on those calculators, for whatever reason, if you have too many cosine terms that you haven't multiplied out, it says memory error, and I don't know how to solve that. So you make sure that you practice these enough on your calculator, not Desmos, not on the computer, not just looking up the answers, so you know how to solve them without getting errors. Okay, so I just multiplied that out, and then as I'm thinking of that, big fat warning, I know it's a pain in the butt, because in math you want to be in radians, you got to change to degrees, or multiply by a conversion factor, whatever pi over 180 is, but you've got to set your mode to your calculator to degrees. So you may want to have your, if you've got to, put your 83 in degrees and put your 89 in radians. Okay, hope you're writing this down because we're going to go to the vertical column next. Okay, surprise. Now we're in the vertical column. All right, so some of the forces up and down also are balanced. Again, this is not optional. You've got to say that step. How many forces do we have up and down? T2 sine 60, that's positive because it's pointing up. Plus T1 sine 30, that's positive because it's pointing up. Minus mg, that's negative because it's pointing down. Okay, and then we solved for T1. T1 is equal to 0.577. T2, be careful, don't drop the extra stuff. It's tempting to do that because you already have stuff there. And then this is 0.8 times 9.8 equals 0. And now we only have one unknown. When you multiply everything out, I'll show one more step just because sometimes people do so much on the calculator, I'm not yelling, that they forget like distributed properties. So you get T2 times 0.7885 equals 7.84. Divide both sides by 0.7885 and you get T2 equals 9.94 newtons. Again, that does not have sign to it because it's just the magnitude of the vector, which does not have a negative sign. So check your work. If you ever solve for a tension or friction and you get a negative sign, what it means is you chose the wrong direction. You assumed friction was going to the left and it was going to the right. Okay, so that's T2. We are almost done, folks. Hang in there. We don't know what T1 is, but psych, we do. T1, I'm going up to the upper right, T1 is 0.577 times T2, or 0.577 times 9.94 equals 5.74 newtons. All right, so this is 5.74 newtons, this is 9.94, this is 7.84. You cannot check your work by saying, let me add 9.94 plus 5.74. Those are clearly way more than 7.84, right? The 9.94 is more than the 7.84 alone. You could take these numbers and plug it back into either of your beginning equations just to make sure that you didn't mess up the algebra. Oh, and then please remind me in class, there's a goofy tug of war demo that we can do, which I don't have on the syllabus right now, so please, if you're interested, please remind me in class. But that is how you do equilibrium problems. Set up horizontal and vertical columns, get a system of equations, solve for what you don't know. All right, hopefully that makes sense, and we'll be practicing that in the next couple days. Warnings are watch your plus and minus signs and make sure you're in degrees. All right, I will see you in class.